President Oaks. Let us remember desire to dictate priorities, priorities shape choices, choices determine actions, and our actions and our desires cause us to become something. Whether a true friend, a gifted teacher, or one who's qualified for your life. So I chose this for today because we're going to be talking about architectural acoustics. We're going to talk about how it sounds in different listening spaces and what contributes to those sounds. Okay. Now, from here on out, almost every day of our class is a whole field that you could specialize in and do your whole career. Okay, so it's you have survived the majority of the intro physics about sound. Okay, so pat yourself on the back. Congratulations. Okay, we're going to use those principles now over and over and over in different applications. Okay, so today we're doing a little foray into architectural acoustics and thinking about what it is about listening spaces that makes it sound certain ways. So all of those choices that are made determine how the listening space is going to be. Okay, so just to begin with, we're going to share some observations about listening spaces from your learning activity. Okay, let's see, Katie Gifford, are you here today? Hi, Katie. There you go. All right, tell us about your learning activity and observation you had from your two spaces.
I just used my bedroom and my bathroom, and I noticed that the bathroom was like more echoey, kind of, probably just because like the tile on the wall and stuff.
Yep, exactly. So many of you did do your bathroom and your bedroom, and the bathroom is more echoey because of the tile, right? Okay, good. And Monet, Blade? Yeah. Tell us why the bedroom is not as echoey.
Well, I did like a front room where it had like
Front,
couch
yeah.
and pillows and stuff,
Yeah.
and it's carpeted, so it absorbs the sound more.
Exactly. It's all of those things she mentioned, bedrooms or front rooms, carpets, couches, beds, pillows, all of the clothes hanging, in the closet, all those things absorb sound more than tile or hard floors. Okay, good. Okay, Jenna Grimillion. Are you here? Okay, Jenna, tell us about your laundry room experience. What did your laundry room look like and how did it sound?
It's partially unfinished. So there's like a concrete wall and so
A lot of echoes, right? Because again, those concrete is a very super reflective surface. Good, good. Okay, and Maria. Okay, yes. So, so tell us about how all of that ties into the concept of reverberation, time that we talked about last time.
So we have that list of all the materials and things that we've been using. And a lot of the materials are either in the room or not in the room. And I noticed like if there were materials similar to the Gabriel longer. That room was.
Okay, very good. So she said you could kind of think about it in terms of the table that we worked with last time, right? If those absorption coefficients were low, then in the reverberation time equation, you're dividing by a lower number, right? Which corresponds to a longer reverberation. So you're just experiencing what we were calculating using the table. So you can see this. Yes, please.
So would a bathroom have a lower reverberation time?
It has lower absorption, which means, and the absorption's in the denominator, so it has a longer or higher reverberation. They're inversely related, the total absorption and the reverberation. Thank you for clarifying. Good. Other questions? Okay, good. You guys did a good job. Thank you for sharing. Okay, so today we're going to talk about different kinds of things that are not so good in concert hall spaces or other things like that, and then some that are really good things like really good concert halls and stuff actually strive. Okay, so here we have A, B, C. Can you see that? Different paths. Okay. All right. So question is, which of these paths are showing these different things? So how would you think about an echo? Like what causes an echo? Tell us what causes the echo. Yes, please.
So I think it's like when the sound wave goes out and reflects off the surface and then it comes back to you. You just hear, like with the sound delay, your own sound.
Exactly. So you have the sound that goes out and comes right back to you. So say you're on a stage. Has anybody ever performed where there was a really bad echo? Like you heard a delay? Yeah, tell us about it.
Yeah, it just kind of made it a little confusing because you kind of, if you listen too much to the echo, then it would like change how you sing or like how you perform. So you just kind of have to like hear it in there, like what you're hearing, and maybe
Right, those little in-ear like monitor things are really good in those spaces. How about you? Tell us about like what kind of space were you in when you heard?
Well, it was just an auditorium and it was like a poorly designed one, obviously, and it was difficult to sing because it would mess up your timing. And then when you have your microphones, then it like picks up on feedback and stuff, and it just like it's just the wrong echoes with what you're singing. So it's just kind of a hot mess while you're performing.
Yes, definitely a big mess. Okay, yes, please.
If you're playing in marching band and the stands are maybe something really reflective, then it's just kind of going all over the place if you're not listening.
Right, so you have to be very careful to use your eyes, right? Especially stay on beat time and listen to the people right next to you and discern those echoes. So generally, echoes can be fun, you know, if you're in a canyon and places like that, but they're not a desirable effect in an auditorium or a concert hall. Okay? And we're going to define echoes in our class as sound that comes in within, you know, in a long enough time that you can tell there's a delay, okay? Because our ears will sum up over a certain amount of time, and all the sound that reaches them in a certain amount of time kind of add to the original sound, which is used in sound reinforcement a lot. We'll talk more about that next time. So echoes have to be far enough that they actually, it's the same sound coming back. Okay, sound focusing. What's the idea of sound focusing? Does anybody remember? We talked about this today. We talked about reflections. Any examples of places you've been where you've experienced this concept of sound focusing? Yes.
There's like a museum where I'm from in Georgia, and they have like a curved roof. And so if you stand on one side of it and you clap someone in like a specific spot on the other side of the room, you can hear it really loudly.
Right. So domed surfaces. Yes.
In the Las Vegas temple, they have, it's like in one of the rooms, and it's like a dome above, and so you can sit on one side of the couch, and then across the room, you can whisper. You can hear.
Yeah. Whispering gallery. Yes.
Cool people outside the JFSB, if you stand right in the middle of that, there's a roof panel reflect off of it.
Oh, yeah. In the JFB. Right. So any of those kind of reflections off of curved surfaces focus the sound to certain spots. Typically, you don't want that in a concert hall type experience because you don't want one seat to be super loud and other seats to be super quiet. The pin drop experiment in the Tabernacle, has any of you seen that before or heard it? I guess. Anyway, that you have to stand in a certain location and the pin has to be dropped in a certain location for you to hear. Right. So has anybody sat in the upper rows of that Tabernacle? Can be very noisy because you hear all of the audience noise from the other side. Bounces off to you. So no whispering up there unless you want people to understand, or in planetariums and places like that. Sometimes subways, like in New York and stuff, there are subways that have those domes, and if you stand against one wall, the person on the other side can hear you even if it's loud. So that's what sound focusing is. So it's a fun thing, but it's not a good thing for concert halls. All right. Sound shadows. Anybody have an idea what sound shadows is? Or which of the rays here would kind of, or areas here would kind of have sound shadows? Yes, please.
Does it have to do with
Yes, so the idea of constructive interference and there being dead spots is this one called dead spots. So that's slightly different. And it is where you have certain frequencies, you have just nodal lines or planes or points where you won't get that frequency of sound as loud as other places. So the dead spots do come about because of that destructive interference thing. Yeah, that's exactly right. Okay. All right. Oops. Sorry, I gotta go back. Okay. And then, but sound shadows are where there's actually something blocking most of the sound. Have any of you ever sat under a balcony that was like too long and felt like the sound wasn't as enveloping or whatever as if you sat elsewhere. Anybody ever felt that? So nowadays with the electronic sound reinforcement, they usually just put speakers under the balcony to help fill in all of that. So it's not as big a deal. But that is why in really nice concert halls, Ravenel Hall is this way, a lot of ones back east. The idea is that you want short balconies. So the people who are sitting under them get the direct sound, but they also get some bounces around. So we'll talk about it a little bit. So sound shadows are when something like a balcony blocks the sound. Okay. And then there are flutter echoes. Okay. All right. So can anybody sitting about in the middle of our class clap really loudly? Okay. Okay, everybody listen. Try again. One more time. Okay. You hear kind of a little bit of a buzziness. Okay, racquetball court, but thank you very much. Good job. All right, racquetball, that buzzy in the racquetball court, that is also an example of a flutter echo. Okay, and it comes because you have reflections off parallel walls that bounce a lot of times. Okay, so parallel walls will give you that rapid low amplitude kind of. Let's see this. Here's before and after just. Now they put absorbers on the wall. Get that difference? So that difference was because instead of having hard reflections off those walls, then the sound was absorbed when it hit the walls. Okay, and that reduced the reverberation time and decreased the flutter.
Does the frequency affect the flutters?
Yeah, so typically it's the lower frequencies that will travel longer or farther than the high frequencies. All right. Let's see where else we are. Okay, so any questions about these defects? That's just another example. Yes. Yes. Okay, so did we look at this box thing last time? Okay. So the idea here is just like waves on a string, okay, where there are nodes and at certain frequencies, there'll be nodes if you're just exciting that frequency. Rooms have nodal lines or planes. And those are places where there's at certain frequencies, there will be destructive interference. Okay. And so you don't want somebody in this seat in the auditorium to not really be able to hear 300 hertz very well. Okay. Whereas the person a few seats over might be able to hear it very well. Okay. So you would typically avoid those kind of room modes. But this is also the secret as to why you sound so good in the shower. Because there are very strong room modes there that emphasize the frequencies that you're seeing. But in concert halls, it would not be it. And you're gonna, when you have lab 5, you get to go to the reverb chamber and they'll put a subwoofer in a corner and they're gonna put it at a natural frequency of one of the standing wave patterns in the room. And then you can walk through it. So you can hear how it gets louder and quieter. Okay, that's it. So, okay, good. Anything about sound focusing? Yes, please.
It's not necessarily
Okay,
sound
sure.
focusing. There have just been times I've noticed that like I'll be sitting somewhere and there'll be a sound happening in front of me, but because of the echo, it's like I'll like look over behind myself because it sounds like it's coming from behind. Is that one of these, or is that something else?
Yeah, so that can really happen. It also has to do with how our ears localize sound, which we'll talk more about when we do our ears. But distinguishing front back location is actually really hard for our ears. So if there's a particularly loud reflection, it might feel, or we might sense that it's coming from there. Okay. Other questions? How are we doing on these defects? Like I said, there are lots of words on these slides that you can look at. Right. This is kind of a summary, but before I show you that, I want to talk about. Okay. So, like I said, there's lots of rooms. Okay, so let's talk about some of the best concert halls you've ever been in and what made them really good. So who's ever been to a really nice concert? Tell us about one of them.
So I had a chance to perform in like a couple different festivals, and one of them was really cool because it looked like the walls were like weaved like a basket, if that makes sense.
Yeah.
So it's kind of like what they were providing. It was really cool, and it sounded really awesome.
So they had some kind of acoustical treatment, right? So that's the trick, is how do you make your acoustical treatments not just look like, you know, big panels, but how do you make them look artistic, right? Plus the weaving pattern probably would diffuse the sound, right? But might absorb some of the sound. So there's that nice, interesting balance. Yes?
Probably nice concert hall. They can actually adjust like the ceiling. Should be
Yeah, so they have adjustable acoustics concert halls. So basically the idea is that, you know, you might have a listening space, a concert hall or an auditorium where you want to have lectures and you want to have movies and you want to have solo performances and you want to have orchestra performances and opera. And the optimum reverberation time for all of those things is different. So if they're all in the same hall, some of them will sound better than others. Right? Have you experienced that before? We go to the same place and some things sound better than others. So they have this variable acoustics approach. And some of them include, right, if it's just a soloist, you don't have the big orchestra band shell, right? You just have something that's more closely, say, around the soloist, like a grand piano or something. Lower the ceiling so that it pushes more of the, reflects more of the sound back out into the audience, right? There are some places that even have adjustable panels on the walls to where you have basically slats that will, you know, come out to make it more reflective or, be retracted so it goes into the absorbing material, right? So that really changes the reverberation time. Even just putting the band shell upright so the sound doesn't go so much to the wings like it does on some other kinds of performances, the big deal. So yeah, so all of those things can be taken into account. Good. Any other thoughts on that? All right, so let's look at this list and see what questions you have about what these things mean or why they are helpful. We talked about noise, right? So say you're in your concert hall, what would be an example of external noise? Yes.
like traffic outside.
Traffic outside. Did you have another one?
That was the
Okay, yeah. So traffic outside, right? Or, even just somebody talking really loudly, right? As they're coming, if they're late, talking really loudly as they come in, whatever. Anything that's outside of the doors. Right? Would be external. Okay, what are some examples of internal noise to the concert hall listening space? Audience talking to each other, right? Any other pet peeves? Yes. Air vents, right? So you get the shh, the air turns on. Sometimes in really nice concert halls, they don't really have just your traditional like one air vent blowing a lot of places. They'll just have kind of like under the seats, a big open, like a wider trench. It'll just let the sound come in without so much of that. Yes.
Cell phones.
Cell phones, very, obvious one there. People unwrapping their mint or their cough drop, right? All of those things are internal. Okay, by defects, it means none of those things we listed on the other one. No sound shadows, no sound focusing, no strong echoes, no dead spots or flutter. What do you think uniform sound decay means? Talk about what do you mean by that? Yeah, please.
The sound dies out altogether, and so you're not just having like one frequency continuing longer than the rest of the frequencies. Like uniformly, they're all going to die out at the same time.
Yeah, so she said uniformly everything dies out at the same time. Okay, so there is a natural high frequencies tend to die out sooner than low frequencies, right? But throughout all of the seats, right? You want all of the seats in your listening space to have sound, approximately the same, have kind of the same reverberation time. And how do you think you get that? What do you think is the key to having that uniform sound field that kind of decays, so everybody hears the cutoff, the last note, and those clap at the same time?
Anechoic features.
Yep, so anechoic features would do the absorbing, yep. That's good. But also the diffuse reflections, right? That idea of irregular surfaces that spread out the sound. Okay. Optimum reverberation time we talked about the other day. Questions about that? Okay, take 1 minute and tell your neighbor the order from shortest to longest that you're supposed to memorize for your test. See if you can do it. Shortest time is B. Next would be chamber music or small ensembles, then opera, then orchestral music, then organ music. Okay, so that exercise of recalling things, it's the way you learn the best. Yeah.
This would be like a really simple question, but does reverberation time in echo, does the reverberation time determine if there's an echo?
Okay, very good question. So reverberation time is the sound bouncing around. And so it's related to how long the sound bounces around. The term echo in terms of a defect is when you have this really sharp, regular surface that's getting it right back to the same place it was, as opposed to diffuse reflections that are spreading out all over. Does that make sense? So yeah, so when we say echo is a defect, we're talking about it just going out and coming right back to the same place. Good clarification. Yes.
Should we memorize these of speech, small ensemble?
Okay, you don't have to memorize frequencies. You don't have to memorize the times on the table. You don't have to memorize any of that. Just that order, right? So you just get in your brain that, this is kind of what, shorter or longer. And then the idea that larger spaces can have a larger optimal time than smaller spaces. So just those two trends are what you need to remember. Okay, good. All right. So these other good methods here, if you can get your audience closer, right, then that's a good thing. So for example, so I've attended this last fall, the Utah Symphony here at the Dijon and at the new Norda Theater over at UVU. Has anybody been to that Norda Theater? It's amazing. Would you agree? It's amazing. And because it is small, like it may be the audience size may be a little bit bigger than this room. And then you've got this stage. Like you are right there, no matter where you sit. It is a completely different experience with the Utah Symphony. Do you agree? Yeah. So it is really quite incredible. And they actually designed, we went to one of the first performances of the Utah Symphony there when it opened, and they actually designed that space specifically so that it would be really good for the Utah Symphony to come down here to Utah Valley, because they travel all over the state. And so, a lot of things were taken into consideration when they did that, but it really is a phenomenal listening space.
So I work for art production.
Yeah.
So I put the shell up in the Dion like a bunch of times.
Yeah.
Something I think is interesting about this space is how adaptable it is.
Yeah.
But I've also noticed that our shell has like, it's bumpy.
Yeah.
It's almost like egg carton. And I'm always curious what acoustic purpose that serves.
Yeah, so that shell, that orchestral shell is bumpy to do diffuse reflections, right? Because if it's just flat, or worse, if it was curved, right? Then it would focus all the sound to like one seat. So you don't want it to be curved. Curved is bad. You want the reflections that come off the music, off the instrument music, right? You want them to be spread out. Reflected back to the audience, but very spread out. So, and it is a great shell. It does have some of those adjustable features, right? Depending on size of the ensemble and the sound you want. All those kind of things. And the new music building is going to be super exciting. Does anybody know about that? Yes, please.
It's gonna have a room that has, well, theoretically, equal sound of like surrounding the stage.
Cool. So kind of a more of a theater in the round type thing, but with music?
Yeah.
Oh, wow. So that will be something really to look forward to. So yeah, they have acoustical consultants that are working with the people who are doing the designing and taking into account, all of these things to have different optimum configurations for different rooms. So, yes, please.
My uncle is actually working with a company that has designed like the acoustics for that building.
Oh, good.
And
Yeah.
he said it has like some of the biggest pieces they have ever made. Like specifically like sound good and all that stuff.
Yeah, so it is going to be top notch. It's very exciting stuff. So they're going to take into account all of these things and many, many more. But okay, so from this bottom list here, any questions about what those words mean? Any of them that you would like examples of? What is a raked floor? So it's like in this classroom where the back seats are higher than the front. Why is that a good acoustic thing for your audience? Yeah. Big stretch. You want to answer? Why would raked floor? Yeah, why a raked floor would be good.
Well, it just helps spread the direct sound.
Right. And it helps to just put people's ears above the person in front of them, right? Because if you're sitting right behind somebody, their head is like a big object for high frequencies. Okay. For low frequencies, it can diffract around, but for high frequencies, it's going to be a big object. So if you get your other people's ears above the person in front of them, then that improves the listening. Any others that you would like to talk about? The advantages or what those words mean? Yes, please. Okay, so reflecting surfaces, but they need to be irregular reflecting surfaces. Yeah, so irregular reflection. Was that your same question in the back? Yeah. So, okay, think what is a space that has not many reflecting surfaces? Where have you been listening or performing that has very little reflective surfaces? Yes, please.
Acoustically treated studio.
An acoustically treated studio, right? They do not want all of that extra, right? They want the direct sound and then they add the reverb in the actual mixing, right? Okay, good. Anywhere else? Yes.
Like in an amphitheater outside.
In an amphitheater outside, right? Because that sound goes out. If you're lucky, you've got a little reflections close by the stage for the performers to hear each other, but then it just goes out. Yeah.
A soundproof room.
And soundproof rooms, right? And in that case, the sound would be almost all absorbed by those walls. Good. Okay. Is this kind of helping you see the differences between these different kinds of things? Okay. All right. So now we're going to talk about, and I think these are on your handout here. Okay, so that was the first side. Okay, so now we're going to do this kind of how do we connect things we can measure with things that we perceive. Okay. And so there are, again, these slides have lots and lots of words, but we'll just try to kind of go through it. Okay, so reverberance is the perception, right, of reverberation time. We say it's a very reverberant space. That means you're saying it has a long reverberation time. So, but the thing you would measure would be the reverberation time. But the thing you're sensing or feeling or detecting, perceiving is the reverberance. Does that make sense? Kind of how to tie those together. Okay, so here are some examples of reverberations. Okay, so what they've done here is they've taken a dry recording, anechoic recording, and then with their computer models of different listening spaces, they play that sound into that listening space and then record what it would sound like, changing the reverberation. But it's all done with a computer simulation. But that's why they can, know exactly what this is. Okay, so here we'll just listen to little bits of these. Okay, this is the dry anechoic recording. so that's what it sounds like. I mean, it's okay, right? Does it sound great? Not great. Okay, so now this is a low reverberation time space, 0.46. Is that better? Better. Okay, let's listen to the 1.4 second reverberation time space. Is that more how you think it should sound? It sounds blending a little bit, maybe. Especially the longer part. Okay, but here's one that's really long, 7.67 second reverberation time. About our empty anechoic chamber. That doesn't work, right? That doesn't work, okay? All right, so that's a string quartet. So that would be a small ensemble. That would be the chamber. Okay, and then here we have speech, the same idea.
In doing so, he became the founder of modern acoustical engineering. He went on to design the acoustics of Boston Symphony Hall, still considered one of the best halls in music in the world.
Okay. All right, so here we go. Now that was dry. Now reverberation time 0.46.
In doing so, he became the founder of modern acoustical.
Does that sound more like you're in a room than the first one? Okay. Okay. And then here's 1.47.
Doing so, he became the founder of modern acoustical.
So already that one gets pretty rough, right? This is the 7.6. You don't need to do very much of that, okay? But that just is to help you remember, like, what does that mean when we say the optimum reverberation time for speech is lower than for small ones? Okay. All right. But you really do detect the room in the speech, and that's when you went in the anechoic chamber. Could somebody describe this sensation? Like, what did you perceive when you went into the anechoic chamber? How would you describe that? Was it different experience? Yes, please.
You could hear the sound, but it would just fall flat.
Yeah.
I mean, obviously it's reaching your ears, but it almost felt like it didn't because it was just so, it would just stop. It felt.
Right. It felt like it just stopped, like it almost didn't reach your ears. And that's just because we are so used to in our everyday lives getting the direct sound and reflected sound, that when you take away those reflections, it perceptually is a very different experience. Yes, please.
This is kind of claustrophobic, like a little bit anxiety inducing, because I think the only time I've ever experienced that
Yeah.
is that if I'm in a very tiny space.
Oh.
It felt like I would be pressing on from all sides.
Yeah. Well, I'm glad you're okay. You're right. But you're right. It does feel like that. Yeah. Yes.
Something that was sort of interesting was, like, obviously sound dies off as things get farther away, but in there it dies off so much faster because there isn't as much echoes. And so I found it so interesting how much softer someone was when they were like twice as far away than when they were closer, because it's not the same degree of like sound change.
That we're used to, right? We're used to, okay, yeah, you're farther away, it's quieter, but that whole, it's 6 dB less, that's really assuming an anechoic environment, right? That just the doubling of distance is changing. Very good. Okay, thank you for sharing those. Okay, good. All right, we'll just keep going through these audio examples because they're so fun. This one is about clarity, okay? So clarity is the third one here on your space. Let's go ahead and do number 2 so we don't go out of order. Envelopment, how would you describe the perception of being enveloped by the sound? Like, or do you have a space in mind where you felt envelopment? That can help us kind of think about that. Yes, please.
Is it like a movie theater that has like all the speakers around?
That is a good example, movie theater, because you've got loudspeakers all over, right? You're in the middle of the sound, right? Okay, lateral reflections is what contributes to our feeling of envelopment. It's the thing you could measure that would contribute to that. And that lateral means from the side. Right? All right, and then clarity. Here is different clarity factors. So clarity is defined by the ratio of the early reflections to the late reflections. Because the sound that comes in early kind of just helps it sound louder. And the sound that comes in late can be distracting, right? So here's the dry recording of this trumpet song. Those are just to help you understand how the clarity changes things. Okay. Okay, so here we go. Sorry for the surprise. Okay, so this is something with very high clarity. So you can tell it's in a room, right? Now less clarity. How would you describe the difference there? It was different than having too long a reverberation time, right? But what was different?
The notes weren't as sharp.
They weren't as sharp.
Yeah, the sounds weren't ending as nicely.
You didn't really hear those beginnings and endings of sounds. Very good. And here's a really bad one. With almost no, enunciation of the whatever the right word is, of the notes. Okay, so that's clarity. Yes, please.
So that means that a greater clarity is needed more early reflection.
Yes. So greater clarity is if the ratio of early to late is larger. They have more energy in the early reflections than in the late reflections. And that depends on a lot of different things, but that's what they're measuring. Okay, ensemble. Okay, how would someone describe for us the sense of ensemble? What are some good words that people could think about if they don't know what that means? Think of it. When have you had a really good sense of your ensemble, and when have you not? Sometimes the contrast is easier. Yes, please.
Ensemble is kind of like a sense of togetherness. Like as a performer, when I played in the orchestra, there were some places we played where I couldn't tell what the other sections were doing. I knew we were supposed to be together and we were almost in the same spot, but I couldn't place it exactly.
Right. So what she said was exactly right. It's the sense of being together with the other musicians, that you can hear the people on the other side of the orchestra, that you can tell that you're all together. You have this sense of playing as an ensemble. Okay. And so that sense of an ensemble really depends on early reflections to the performers. Okay, that's one of the main reasons, one of the reasons why they do put up things like band shells or orchestral shells or lower the ceiling or whatever it is, so that they get more energy in those early reflections to the performers. Yes.
So is it kind of the ability to hear different sounds from different places,
Within your ensemble?
Yeah.
Yeah. So not the whole concert hall, but just within the ensemble.
Okay.
Yeah. Okay, questions about that? So if you're used to playing, say rehearsing in a small room, right, or garage or whatever, where you have lots of reflections of surfaces that are relatively close by, and then you take those same people and they go outside on the grass and play, right? Their sense of ensemble, of being able to hear the other performers, will be much, much less outside, because there aren't those reflections, early reflections.
So in women's chorus last semester, we sang at the Madeline Cathedral.
Okay.
And I'd be standing next to someone and we'd be shoulder to shoulder and I couldn't hear them. Is that the same thing?
Because there's so she said that the women's choir performed at the Cathedral of the Madeline up in Salt Lake, but she couldn't really hear the person beside her. Was it super tall ceiling?
Yeah.
Super wide space? Right, so you didn't have any of those early reflections coming to your ears, but she's saying this way, not in your ears, right? So yes, that you would have a lower sense of ensemble in that case. Okay. All right, so here are some examples for what is called intimacy. Right, this is like the relationship between the audience and the performer. So here's the dry recording. I'll try to stop. Sorry. Okay. All right. So that had an initial time delay gap, okay, of 6 milliseconds. So initial time delay gaps means the time between the, like, how much sound comes in that first, like, 30 milliseconds. So there's the direct path and then some reflections, relatively early reflections, but this is between the performer and the audience. So here is a longer initial time delay gap. And longer. Okay, and longer. Okay, and super long one. Okay. Sorry, this first one was the anechoic. This was the 6 millisecond initial time delay gap. Okay, so which one? Yeah.
Does intimacy affect clarity? Because to me, they sound really similar.
Yeah, so does intimacy affect clarity? So it can, right? Because the clarity is the ratio of energy in the early to the late reflections. But intimacy is kind of like, we call it the initial time delay gap between that first bit and the other sound that comes in. And so the, you want, I don't know if you could sense, but it kind of sounds like you're in a bigger room as that initial time delay gap gets large. Does that make sense? Like you're not as intimate or up close to the performers. So that's what it means, is how close to the performers you get, to the audience.
And what would be like the difference, actually, never mind. That's just like the time of the initial sort of first reflection.
It's the time gap between your initial 30 milliseconds, what you get in the first 30 milliseconds and the next arrival. It's the gap between those guys. Okay. All right, and then this is warmth. So first the anechoic recording. All right, now that's just dry. Okay, now this BR stands for brilliance. So brilliant sounds are different than warm sounds. Those are like opposite. So the brilliance is going to increase as we go through this. Okay, so this is brilliance of 0.44. Okay, now we'll go to this one. Now we're going to go to this one. I'm going to go back to this one and let you listen to that last part. Does it sound like that had more low frequencies? These speakers are not really doing it justice, but warm sounds is like how much the low frequencies stay around. So reverberation time is a function of frequencies, and the sound feels more warm if you have more low frequency sounds staying around for a longer time. All right, and then spaciousness, this idea of spaciousness. Okay, so again, the spaciousness idea refers to, like, if you're outside, you would have a very high feeling of spaciousness. If you're in a very small space, like a practice room, right, you would have a relatively low sense of spaciousness. And the thing that we can measure that correlates to that is called the binaural quality index. So binaural means 2 ears, right? So how similar is the sound between your 2 ears? So will the sound be more similar in the practice room or outside? In the practice room, right? So that's the idea on the binaural quality index. Okay, so here's the dry recording, which is kind of like outside, no reflections. Okay, versus one with the lower binaural quality index. Right, so it feels like you're in a space. Okay, the other demo I have is just loudness. Concert halls also have something that's just called gain, which is just corresponds to the loudness. So we'll just do a couple of these. So this is with the gain of the Compton Verney Opera House. And this is the gain, a larger gain of the Vienna, I would say, music in Saal. And then the Grundrigs Cathedral gain. There's also extra reverb time there too, but gain corresponds to loudness. Okay, so we've gone through these, but like I said, the words are all here. Okay, on the slides. Okay. I'm sorry, the initial time to play gap is the time between the direct sound and the first reflected. And if it comes in within those first 30, 35 milliseconds, then it is a good concert. Just the difference between your direct sound and your first reflections is that initial time delay gap that gives you the feeling of intimacy if it's short enough. Okay. Questions? Yes, please. It's just this, what relates to what. And if you know what these words mean, it's a little easier to remember why they would relate to these things. Does that make sense? But none of the numbers are going to be on it. You don't have to know any of the numbers, just the ideas. Okay. All right, I'm not going to make a video for this one because all of the words are on the slides. I've made a video and said all the words again, it will just be repetitive. Okay? Friday.